This week we're going to be discussing the TCP/IP transport layer protocols. So while TCP/IP's network layer protocols provide network access, routing, and delivery functions, TCP/IP's transport layer protocols provide the mechanisms that are necessary to move messages of arbitrary sizes from senders to receivers across a network. While TCP is arguably the most important than any of the other transport layer protocols, for instance, UDP, etc., both of the protocols perform vital roles in enabling the transfer of arbitrary data across a network. So the objectives for this week, we're going to talk about the key features and functions of the user datagram protocol and transmission control protocol, so UDP and TCP. We're going to explain in detail the header fields and functions of a UDP packet, as well as port numbers, processes, and how UDP behaves when used as a transport protocol by IPv6. We're going to explain in detail the mechanisms that drive segmentation, reassembly, and retransmission for TCP, as well as how TCP behaves when used as a transport protocol by IPv6. We're going to describe how UDP and TCP pseudo-headers are organized with the IPv6 header and extension headers. We're going to discuss the differences between connectionless and connection-oriented transport mechanisms. And we're going to learn how to choose between using UDP and TCP. So when we talk about UDP and TCP, they function as peers. If all applications required a guarantee of acknowledged delivery, then the only protocol you would ever use is TCP. But TCP comes at a cost of time and bandwidth because it provides a connection-oriented, reliable transport layer addressing. It manages acknowledgments, which consume time. It asks for the various statuses of a message, which consume time and consume bandwidth. IP operates at the network layer of the OSI model, so it's responsible for transferring variable length data sequences from a source host to a destination host. And like we said, TCP guarantees acknowledged delivery. When we talk about things like video and voice, though, we can drop packets, right? We're not concerned that everything gets through, but that the vast majority gets through. We need a wider pipe. We need more bandwidth. We need less time in the header acknowledgement and the processing. And UDP gives us that gain in speed and a reduced use of network bandwidth, increasing the time to get from point A, or reducing the time to get from point A to point B for a packet. So there are certain needs that UDP is really good for. So you can think of UDP as no-frills transportation. It's the Uber X instead of the Uber Black. UDP is a connectionless protocol. It's a simple kind of transport service. Package messages that are taken as is from the TCP/IP application layer into datagrams. UDP is used by applications that contain their own connection-oriented timeout values and retry counters, and it runs up to 40% faster than TCP. With UDP, the applications are responsible for that guarantee of delivery. So if you're presenting a video presentation on the network, the application software has to have the abilities to get the packets where they're supposed to go. UDP just provides the bare bones back end for the data to roll on. And in terms of higher layer protocol identification, remember we talked about ports in some of the beginning lectures. We're going to see the role they play now regarding data transfer in a bit more detail. Now, conversely, and before we jump to TCP, this is an RFC 2460. So this specifies how UDP operates differently over IPv4 than over IPv6. So let's jump to TCP. And here's a screenshot of netstat. All right. So TCP is connection oriented. So applications rely on the protocol to ensure a level of reliability. So applications rely on data reaching its destination when they use and choose TCP. TCP offers connection-oriented services with sequencing, error recovery, and a sliding window mechanism. So because of TCP's end-to-end reliability and flexibility, it's a preferred transport method for apps that transfer large quantities of data that require reliable delivery services. Now, UDP and TCP don't have v6 versions to match IPv6, but both protocols are essentially unchanged in terms of providing transport for IPv6. But IPv6 may make different use of TCP depending on its requirements. So we talked about IPv6 jumbograms. That's an example. So here's an example of packet headers and different protocol layers. And here's an example of running netstat for TCP stats over IPv4. And here's netstat for TCP stats for IPv6. So just to kind of dispel any confusion when talking about the differences between IP and UDP, because both of them are connectionless, IP functions at the network layer and UDP functions at the transport layer. The key differences in the function of each layer. So the network layer protocols such as IP provide network address routing and delivering, counting on the transport layer or above to provide that guaranteed delivery. Transport layer protocols provide the mechanisms to move messages of arbitrary size from a sender to a receiver on the network. In a sense, it's the difference between the address on a letter and the mail truck itself. When we talk about no delivery guarantees, it's like, a caricature in a comic strip. So it's like, the hero stranded on a desert island. They put a message in a bottle, they cork it, they throw it into the ocean, but there's no guarantees someone's actually going to receive it. Port numbers and the upper layer applications make it possible for UDP packets to actually get where they're going. UDP just provides the ride. And as far as checksums go, they're only used to verify that the UDP packet got there. It's up to the application to take further action. So it's like receiving bills in the mail. The letter carrier delivers them, but they don't respond back to the recipient saying, hey, you opened it and you sent your check back in. And the application, going even further, has to handle the segmentation issues. It has to do everything. So if you anthropomorphize the situation, the application could be saying to itself, if you want to get something done, you have to do it yourself. So we talk about UDP, the characteristics and the limitations here. No reliability, no delivery guarantee, no connection handling. Identifies the application layer protocol, the checksum for the messages carried in the header. No buffer services, no segmentation, but what are you getting for it? Well, it's TCP is 40% slower, so you're getting speed. For all of this, you're getting speed. And if you can reliably do all this, or take the pieces you need and do it in the application layer, you're going to get that speed by choosing and using UDP. So UDP header fields and functions. So when the protocol field of an IP header contains the value of 17 or hexadecimal 11, the UDP header follows the IP header. So the UDP header is short and simple. It's only 8 bytes long. The UDP header's main function is to assign the process, the application that's using the IP and UDP network transport layer. So our header fields here are source port number field, destination port number field, your length, and your checksum. So here's an example of the UDP header format. When we look at the various well-known port numbers, so 53 is DNS, 69 is TFTP, 137 is NetBIOS name service, 138 is NetBIOS Datagram. These are all well-known ports that typically use UDP. And, we see the UDP checksum here. It's optional. It's frequently not generated, so a value of 0 in that block in the header just means the application didn't generate or didn't send a checksum. When we talk about, again, the source port number field, this defines the application or process that sends the packet using UDP. And your well-known port numbers, again, same as TCP 0 through 1023. These are core services that systems offer. And the registered port numbers, 1024 through 49151. These are assigned to various industry applications and processes. And dynamic ports are used as temporary ports for specific communications while they're underway. So just like we talked about in the first couple chapters, ports behave the same way in UDP. And here are, again, some common, well-known UDP port numbers. These are, I think, different than the ones I mentioned. So 67's Bootstrap protocol for the server, 68 Bootstrap protocol for the client, 161 for SNMP, 162 for an SNMP trap, and 524 RIP. So your destination port number field defines the destination application or process that uses IP in the UDP headers. The length is the length of the packet from the UDP header to the end of the valid data, and your checksum field is optional. So for UDP port numbers and processes, both UDP and TCP use port numbers to define the source and destination processes or applications. And when we talked about the destination port number field, the source and the destination port numbers are not necessarily the same within a conversation between two hosts. Now, by default, Windows Vista through Windows 10, Windows Servers 2012, and 2016 support a port range of 49.152 to 65.535. And here's an example of the max user port registry setting that stores that value. And here's an example of TCP and UDP communications that are forwarded to an application layer protocol based on the destination port. So the UDP header format was not specifically updated for a newer version to coincide with IPv6, as I mentioned before. IPv6 treats UDP as an upper layer transport protocol, so it manages UDP in accordance with its requirements. So UDP hasn't changed, but IPv6 and IPv4 treat UDP a bit differently. All the information for UDP headers, port numbers, and processes that are valid under IPv4 are all valid under IPv6. So here's an IPv6 pseudo header for UDP. Now we jump to TCP. So again, Transmission Control Protocol, one of the core protocols that allow the transport layer services for large networks, including the internet to work. It's one of the original protocols at this layer that works with IP. It provides reliable transportation network traffic from the source to the destination, and it's responsible for providing ordered delivery of a stream of bytes from an application on one network node to an application on another network node. So unlike UDP, the application doesn't have to handle all this. TCP does, but at a cost of time and bandwidth. And communications between two computers that are being established through TCP use a three-way handshake procedure. So TCP and IPv4, the primary functions and features of TCP communications. You have your three-way handshake, so your startup connection process. the Keep-Alive process, connection termination, sequence and acknowledgement process, error detection and error recovery processes, congestion control, sliding window, header fields and functions is pretty much the exact opposite of UDP in terms of feature sets. But again, with a cost. So the three-way TCP Startup Connection Process, it's the three-way handshake. If you've ever heard a modem and heard the rather odd combo of tones and noises, that's a connection being negotiated. Here's an example. SYN, ACK. So your 3-packet handshake. So, apparently I'm all... There we go. So this is an example of a packet capture of that handshake, of the first packet. Here is a packet capture of the second portion of the handshake. And the third. So if we flip back, SYN, ACK. And here are both the TCP max connect retransmissions and maximum number of connections registry settings in Windows. TCP half-open connections occur when the handshake process does not end successfully with the final ACK. In my cybersecurity courses, we talk about how this can be used, especially on older servers, to cause denial of service attacks. Half-open connection communication sequence occurs in the following order: SYN, ACK-SYN, ACK-SYN, ACK-SYN. So again, the process doesn't end successfully with a final ACK. So the Keep-Alive process can maintain a connection where there's no data sent across the wire. The TCP Keep-Alives, they're disabled by default on Windows XP through 10, Windows Server 2003 through 2016. The Keep-Alive time setting defines how long to wait before sending the first TCP Keep-Alive packet. The period of Keep-Alives defined by Keep-Alive time in the Windows registry setting is by default 2 hours. So you'll see a value in there, 7.2 million. That's the number of milliseconds. And the Keep-Alive interval setting defines the delay between the Keep-Alive retransmissions when no acknowledgements are received. By default, it's set at 1 second, and that's fairly typical across most operating systems. So here's an example of the Keep-Alive time registry setting. And also, Keep-Alive times are disabled by default in Windows 7, Windows 10, Server 2012, 2016. But the application can enable TCP Keep-Alives on its own. So if you're developing an app, you're welcome to do this. The operating system doesn't handle it anymore, though. So terminating a TCP connection requires 4 packets. Host 1 sends a TCP packet with the FIN and ACK flags. Host 2 will send an ACK in response. Then host 2 sends FIN and ACK, and then host 1 returns ACK. And here is an example and a diagram of that 4-step process. And here are some various TCP connection states. So when a connection is closed, the socket pair, so when we say socket pair, it's again IP address and port number, or just socket. It's placed in a wait time delay state, so it means a new connection can't immediately use the same source and destination port addresses. So that's done to make sure there's no misrouted packets and that they don't get delivered to the wrong address. So the TCP sequence acknowledgement process, this guarantees that the packets are in the right order and have all the segments. So during the handshake, each side of the connection selects a starting sequence number, and each side increments the sequence number followed by the amount of data in the outbound packet. And I guess I'll stress this is super important for TCP because it reduces the amount of potential signal noise, especially when you have unreliable connections over the internet. The data has to be in the right order, and there has to be all the data. Again, because this goes to the tenets of depending on TCP. So all this extra work is just to ensure reliability. Here's an example of acknowledgement sequence numbers. So this basically is walking through the very simple math that's used if you want to go back to the previous slide here. And here's, again, an example of a sequence communication using those increments based on the size of the data. So error detection, error recovery, there's lots of reasons why communications fail, communication sequences fail. A sender's data packet may have been involved in some type of collision. Acknowledgements may not make it back because there's a problem with routing. Whatever the reason, TCP was designed to not only detect errors but recover from errors. So you'll have a retransmission timer. So that's your first error detection, error recovery mechanism. Your retransmission timeout, or RTO, that's a value specified by the timer. And then you have increments. So your first retransmit will be whatever value you have in for RTO. Your second will be 2 times RTO. Third is 4 times RTO. So it's 2 to the retransmit instance minus 1 power times your RTO. So TCP congestion control. So the overloading, so congestion is overloading of a network or receiver, and when we talk about a network overload, it occurs when there's too much data over whatever network medium you're working with. Overloading a receiver happens when the number of data bytes is greater than the advertised window. So that's defined in the window field of the receiver's TCP header, and the current window is always the lesser of what the network and receiver can handle. The receiver window size is the amount of data that can be buffered in bytes on a one-time connection. It can also be thought of as the amount of data the transmitting host will send before waiting for an acknowledgement. And typically, TCP looks at the bandwidth of a connection and then sets the send window to 2 TCP segments to avoid a buffer overflow. All this is in RFCs 1122 and 3390. And here's an example of the network window and receiver window to determine the current congestion window size. In RFC 5681, there's 2 congestion control mechanisms that are defined: slow start congestion avoidance, and fast retransmit, fast recovery. Here's an example of the global max TCP window size registry settings and setting in Windows, as well as the TCP window size registry settings. So these are your default values. So the sliding window in TCP, this is used to determine the amount of unacknowledged data that can go out on the wire from any sender. Don't confuse this with the advertised window, which is the amount of data that a receiver has buffer space available for. This uses the Nagel algorithm. John Nagel wrote RFC 896. We talk about small data segments. When they're being sent but not acknowledged, no other small segments can be sent. You'll see this in things like Telnet, where you're looking at short commands. Silly window syndrome is caused when enough data is sent to a TCP host that it fills the receiver buffer and it puts it in a zero window state. So when you're not sending additional data until the receiving host advertises a window size large enough to receive at least one more TCP segment. So that can be a problem as well. Here's an example of window sizes based on acknowledgments that are received. So your TCP header fields, you have your source port number, your destination port number field, your sequence number field, acknowledgement number field, and header length field. As we talked about before with UDP, some of the packet fields are the same, but keep in mind both TCP and UDP packets are encapsulated in an IP header that specifies the IP routing information. So here's an example of the 20-byte TCP header. And here's an example of packet capture, so a decoded TCP header. And here are various TCP flag settings. And we talked about most of these. Other headers, functions, and fields. You have your window size field, your TCP checksum, your urgent pointer, as well as the TCP options field. Here is the TCP use RFC 1122 urgent pointer registry setting in Windows and its default value. And these are some various TCP options defined through RFC 793, 7323, and 2018. So TCP is, when we talk about IPv6, remains pretty much unchanged as a transport protocol. The only difference is the way that IPv6 and IPv4 treat TCP, and this is what results in change behavior for this upper layer protocol and other upper layer protocols. So just like UDP, TCP has to include the 128-bit address from the IPv6 header. So it has to be modified to do so. Because the checksum calculations for UDP and TCP are mandatory under IPv6, TCP uses an IPv6 pseudo header for the purpose. So again, the pseudo header is built of the source address, the destination address, the TCP length, the zeros, and the next header fields, plus the fields found in the TCP header. So here's an example of the IPv6 pseudo header for TCP. So we talked a few weeks ago about IPv6 extension headers and IPv6 headers in general. So again, IPv6 headers put all the optional data in extension headers, and an extension header contains the optional internet layer data that's stored in separate headers between the IPv6 header and the upper layer transport pseudo headers. So when we talked about extension headers in detail, I really want to clarify the structural relationship between the IPv6 header and the UDP or TCP pseudo header. So here's an example of the IPv6 header with a TCP transport protocol and no extension headers. And here's an example of the IPv6 header with UDP transport protocol and 3 extension headers. So choosing between TCP and UDP, we talked about this at the very beginning of the lecture, but TCP is super robust. You're going to make sure your data gets there, but there is a performance hit. There's a bandwidth hit that comes with it. It carries a lot of baggage, a lot of header fields, a lot of back and forth communications. I mean, just to acknowledge a connection is a 3-way handshake. To close down, there's 4 different steps. There's additional header fields, more meta messages. But when you're talking about video communications, voice communications, TCP's overkill. You're okay with some drop packets. You're okay with some lost communications. You look at Skype, WebEx, GoToMeeting, Zoom. When the internet is basically flooded because of everyone working from home because of coronavirus. This is where UDP actually matters. If you want to think of a real world application for this. If all of this right now was running on TCP during this event, half the stuff wouldn't work. TCP isn't as important as it once was. 2 reasons. Local area networks have increased, but also kind of outside of here, the reliability and ability for applications themselves to take over some of this functionality has greatly improved, especially with some of the software frameworks that are out there. So you can use UDP and you can get some of the reliability of TCP, but with some semblance of the features that TCP provides. So in summary, the transport layer protocols come in 2 types: connectionless and connection-oriented. UDP is connectionless, and it's associated with TCP/IP. UDP header is short and sweet. It has a protocol identifier, optional checksum, source and destination port addresses. TCP is a lot heavier. It's connection-oriented. It focuses on reliability. It's longer and more complex and has many more flags, values, and message types. But it wants to make sure your data gets there, that it has error correction, and it is reliable. Appropriate historical uses for UDP, they concentrate on application services that manage their own reliability and connections, namely video and voice. Appropriate and historical uses for TCP, reliable user services. And while there's no updated versions for TCP and UDP for IPv6, some of the functionality needs to be wrapped up. We need to take into account 128-bit addresses. So sometimes we'll wrap these up in various headers or add pseudo headers on top of it. The functions of these transfer protocols are treated differently when used by IPv4, IPv6.